Hi viewers, welcome to JSM. In previous video, we discussed atomic radius and different types of atomic radius. In this video, I am going to discuss variation of atomic radius in periodic table. So let us see in groups. In groups, what will happen in the atomic radius when you go from top to bottom? Okay, let us see an example here: lithium, sodium, potassium, rubidium, cesium. So francium we are not taking because this is a radioactive element. That's why we are not taking. Okay. Then here you see. So lithium electronic configuration 1s2 2s1. Here sodium 1s2 2s2 2p6 3s1. So here I am writing last electronic configuration. Here 4s1, here 5s1, here 6s1. So when you observe lithium to cesium, shell number what happens here increases. Here only 2 shells are there, here 3 shells, here 4 shells, here 5 shells, here 6 shells are there, orbits are present. So when you see the orbital atom here 2 shells are present. In this case 3 shells are present. Here totally 4 shells are present. So when you see the rubidium 5 shells, when you see the cesium, totally 6 shells are there. 1, 2, 3, 4, 5, here 6. Okay, here 2 shells, here 3 shells, here 4 shells. In the rubidium 5 shells, here I written for cesium, totally 6 shells are there. As the number of shells increases from top to bottom, so radius what will happen? So radius also increases. Here radius is very less because size of the atom is less because of less number of shells. Here radius is more because more number of shells. Okay, that's why what we can say, from top to bottom in a group, as the number of shells increases, atomic radius increases. Number of shells increases, atomic radius also increases. So let us see in periods what will happen in periods. Let us take a period, that is lithium, beryllium, boron, carbon, nitrogen, oxygen and fluorine. So we are not taking neon. So what is the reason? I will explain later. Here when you see lithium electronic configuration 1s2 2s1, beryllium 1s2 2s2, boron 1s2 2s2 2p1, here 1s2 2s2 2p2 for carbon, nitrogen 1s2 2s2 2p3, oxygen 1s2 2s2 2p4, this is 1s2 2s2 2p5. So when you observe the electronic configuration, the newly entering electron or differentiating electron enters into the same shell from lithium to fluorine. That means electron enters into the second shell only, not in the next shell. Here 1s 2s orbitals are there. In that already 1s2 electrons are there. Here 1 electron. Next 1s2 2s2. Next 1s2 2s2 2p1. Next 1s2 2s2 2p2. Here 1s2 2s2 2p3. In this case 1s2 2s2 2p4. Here 1s2 2s2 2p5. Okay, so what happening here, number of electrons in the similar shell increases when you observe the protons in the present in the nucleus. Here how many protons are present? In the lithium 3, in the beryllium 4, in the boron 5, here 6, here 7, okay, here 8, in the fluorine 9. So as the number of protons increases in the nucleus, nuclear charge also increases. When the nuclear charge increases, that increased nuclear charge attract electron which is present in the outermost shell very strongly towards the nucleus. Then size of the atom, what will happen? Decreases. Here only 3 protons are there, that's why nuclear charge is less. But when come to the fluorine, here 9 protons are there. So because of this reason, it attracts outermost electron towards the nucleus very strongly. Then size, what will happen? Decreases. Okay, that's why what we can say, in a period from left to right, as nuclear charge increases, atomic radius decreases. As nuclear charge increases, atomic radius decreases. Here why nuclear charge increasing? Because of number of protons in the nucleus increases. But here electron enters into similar shell. Only in the second shell electrons are increasing, not in the different shells. So that's why here nuclear charge increases when protons increases. That's why size decreases, then atomic radius also decreases. So let us see the variation of atomic radius in D block. Okay, 3D series. So these are the 3D series elements in that: scandium, titanium, vanadium, chromium, manganese, iron, cobalt, nickel, copper, zinc. So when you observe the atomic radius in picometer, here scandium 144, 132 for titanium, vanadium 122, chromium 118, manganese 117, iron 117, cobalt 116, nickel 115, and copper 117 picometers, and zinc 125 picometers. So scandium to manganese, atomic radius decreases, Then iron to nickel, atomic radius nearly same. Then copper to zinc, atomic radius increases. So what is the reason behind this? So let us see. From scandium to manganese, atomic radius decreases due to Z effective is nothing but here nuclear charge. So nuclear charge is greater than the shielding or screening effect. Okay, due to Z effective or nuclear charge greater than the screening effect, from scandium to manganese, atomic radius decreases. Here nuclear charge is more over the shielding effect. Because why shielding effect is less here? So when you observe d orbital here, 1, 2, 3, 4, 5. Up to manganese only 5 electrons. Here 1 electron, d1, d2, d3, d4, d5. d1, d2, d3, here d5 and d5. Okay. So due to the less number of electrons, shielding effect also less. Okay, that's why nuclear charge is more over the shielding effect. So when you observe here iron, cobalt, nickel, so these will show nearly similar atomic radius. That is because of Z effective is equal to nuclear charge is equal to shielding effect. Okay, nuclear charge equal to shielding effect. Then here copper to zinc atomic radius increases because Z effective is less than shielding effect. Here shielding effect is more. And also here we can say one more factor. So due to the electronic repulsions, because when you observe copper and zinc both having D10 configurations, here D10, here also D10 configuration is there. So due to the D10 configuration, inter-electron repulsions are present. So due to that inter-electron repulsions, size of the electron cloud, that means atomic radius, what will happens? Increases. Due to the inter-electron repulsions, size decreases here. Okay. In the first case, scandium to manganese atomic radius decreases due to Z effective nuclear charge is greater than the screening effect. From iron to nickel, Z effective nearly equal to the screening effect. That's why a constant atomic radius values. It means nearly same atomic radius values are present. Copper to zinc atomic radius, what will happen? Increases due to the Z effective is less than the screening effect, and also we can say based on the one more factor. What is that factor? Inter-electronic repulsions due to the D10, that means more number of electrons present in the same orbital. That's why repulsions are more. That's why electron cloud expands. Due to that electron cloud expands, what will happen? Size of the atom increases, then atomic radius also increases. So this is about the 3D series in D block elements. Okay. Next, in D block elements only, when you observe the group wise, scandium, titanium, vanadium, chromium, next yttrium, zirconium, niobium and molybdenum, next lanthanum, osmium, tantalum and tungsten. In this case, okay, here this is 3D series, this one is 4D series, this one is 5D series, 3D series, 4D series, 5D series. When you go from in a group, this is a third group, this is a fourth group, fifth group and sixth group, then seventh, eighth, like that it will come. Okay, when you observe this group, from scandium to yttrium and lanthanum, atomic radius increases group wise. Scandium, next yttrium and lanthanum, size increases, atomic radius increases. But when come to titanium to zinc, atomic radius increases, but zirconium and osmium shows nearly similar size. Vanadium to niobium, atomic radius increases. From niobium to tantalum, they will show similar atomic radius. Chromium to manganese, atomic radius increases, but chromium to molybdenum, this is molybdenum. Molybdenum and tungsten shows similar atomic radius. So what is the reason for this? The reason for this is lanthanide contraction. So what is lanthanide contraction? Here when you observe here, so between lanthanum and osmium, 4F series elements, how many? 14 elements are present. From 58th element to 71 element. So totally 14 elements are present between lanthanum and osmium. In these 4F series elements, electron enters into the 4F orbital, where they are entering 4F orbital. This is the first shell, second shell, third shell, fourth shell and fifth shell. Is a 1s, here 2s, 2p, here 3s, 3p and here 3d, then here 4s, 4p, 4d and 4f, here 5s, next 5p, 5d, 5f, then 6s, 6p. So after filling electron in 6s, after completion of 6s 2, then electron enters into the 4f orbital. When electron enters into the 4f orbital, so this f orbital shows less or poor screening effect. Screening effect of this f orbital very less. So due to the 8-fold structure, okay, due to the diffused structure, this f orbital shows poor shielding effect. when this f orbital having poor shielding effect, so this f orbital does not stop the nuclear charge on the 6s orbital, on the 6s electrons. Okay, the electrons which are present in the 6s orbital not affected, affected morely with nuclear charge. Okay, due to the poor shielding of 4f electrons, the electrons which are present in the 4f orbital, poor shielding of 4f orbital. So why here f orbital shows less shielding or screening effect? Due to its diffused shape, white fold structure. Okay, that's why it shows poor shielding effect. Then it does not stops nuclear charge on the 6s. That's why nuclear charge on the 6s orbital is more, then it attracts the electrons which are present in the 6s orbitals towards it. Then size, what will happen? Size decreases. Then size decreases. That's why osmium size, what we are expecting, osmium size is more, but due to the lanthanide contraction, osmium and tantalum tungsten size decreases than the expected. We are expecting more size, but what will happen? Size decreases due to the poor shielding of 4f orbital. That's why this nucleus attracts that electrons towards it very strongly, then size decreases. That's why this zirconium osmium shows similar size, and niobium tantalum shows similar size, and molybdenum tungsten shows similar size. Okay, the decrease in atomic radius due to the poor shielding, of 4f orbital is nothing but lanthanide contraction. Okay, that is nothing but lanthanide contraction. So what is the definition for lanthanide contraction here? Decrease in atomic radius due to poor shielding effect of 4f orbital. 4f orbital is called as lanthanide contraction. Lanthanide contraction. Okay, this is about the lanthanide contraction. So remember, this is very important pair. Zirconium osmium shows similar size, niobium tantalum shows similar atomic radius, and molybdenum tungsten also shows similar radius. Because of lanthanide contraction, the size of osmium and tantalum tungsten decreases than the expected. Okay, that's why here these pairs will show the similar size.